Acid-base theories. Acids and bases are substances which have specific properties. An acid is generally sour in taste, things like vinegar or citric acid or tartaric acid. Vinegar is self-explanatory. Citric acid is commonly found in citrus fruits like lemons, oranges, limes. Tartaric acid and citric acid are both found in some foods, for instance, sour gummy worms, which you can buy at the grocery store, have a white powder that coats the gummy, and that white powder is a mixture of citric acid and tartaric acid. And it's relatively acidic, which gives it the flavor that it has. The sour taste associated with acids comes from interactions of the acid with proteins in your tongue, which send chemical receptors to the brain, indicating that you've got this interaction with the acidic component of the acid, which we'll talk about in a minute. Acids tend to change indicators: red for litmus, clear for phenolphthalein, and yellow for bromothymol blue. An indicator is a substance which will change its physical appearance in different solutions. So an indicator will be different in appearance in an acid versus a base. If an acid is non-oxidizing, which means most acids other than nitric acid, they'll generally react with metals which are higher in the activity series than hydrogen to form H2 gas. They can also react with metal oxides or hydroxides and will tend to form salts of the metal oxide and hydroxide as well as water. If you take a strong acid and react a strong acid with a salt of a weaker acid, which is the weaker acid without its protons, without its H's, and in place you'll have cations like sodium or potassium, you'll generally form the reverse salt and the weaker acid. So taking hydrochloric acid and reacting it with sodium phosphate, which is a sodium salt of phosphoric acid, will generate sodium chloride, which is the salt of hydrochloric acid, and phosphoric acid. Now, bases tend to be bitter to taste. Alkaloids are organic bases which are commonly found throughout nature and tend to be poisonous. Humans have evolved naturally an aversion to bitter tastes, and one possible reason for this is because many bitter things contain these organic alkaloids, and these organic alkaloids or bases are toxic to us. So the bitter taste is often a response that we have acquired to try to protect us from ingesting poisonous substances in the form of certain organic bases. Bases are slippery to the feel or to the touch, and the reason for this is because if you react a base with an oil, it will form a soap-like substance. So because your skin secretes a natural oil, any reaction that you get or any base that you get on your skin will react with that oil in your skin and form a crude soap, which will give you that slippery feeling. Bases, like acids, will change indicators, but bases will tend to change litmus blue, phenolphthalein pink, and bromothymol blue to blue. They will react with acids to form salts and generally water for a strong base, or a combination of the acid and the base as a salt. Now, acids and bases are both electrically conductive. Acids are electrically conductive because of the H plus ion that is formed. Bases are electrically conductive because they form an OH minus ion in solution. There are three different theories which discuss the nature of acids and bases. Arrhenius theory is the least complete theory. It encompasses the least number of acid-base substances. Bronsted-Lowry theory is the second of the theories. It's the middle in terms of completeness. And then Lewis theory is the most complete theory. They differ in their definition of what an acid and base are, as well as the process of neutralization and any involvement of solvent in the reactions. In order of completeness, Lewis is greater than Bronsted theory, which is greater than Arrhenius theory. So if we look at the diagram below, Arrhenius theory is in the center, Bronsted surrounds it, and Lewis surrounds that. I can move from the center on out in terms of my definition. Something which is defined as an acid or a base by a theory in the inside, like Arrhenius theory, will be defined as an acid or a base by the outer theories. So an Arrhenius acid or base will be a Bronsted-Lowry acid or base, or a Lewis acid or base. A Bronsted-Lowry acid or base will be a Lewis acid or base. I cannot move inward, so something which is a Lewis acid or base will not necessarily be a Bronsted-Lowry acid or base. Something which is a Bronsted-Lowry acid or base will not necessarily be an Arrhenius acid or base. Now, Arrhenius theory was developed by Savant Arrhenius and deals with electrolytic dissociation of acid and base substances. Acid will electrolytically ionize to form H+ ions, and bases will dissociate to form OH- ions. If we do not form H+ or OH-, according to Arrhenius theory, we do not have an acid or a base. As an example, HCl will ionize to form H+ and Cl-. NaOH will dissociate to form Na+ and OH-. Neutralization, then, is a reaction of an H+ with an OH- to form water. Now, Arrhenius theory was successful in dealing with protic acids and metal hydroxides. It was also a good step forward in our understanding of acid-base aspects and laid the groundwork for later theories of Bronsted-Lowry theory and Lewis theory. However, it fails to explain non-protic acids and bases like ammonia. Bronsted-Lowry theory was developed in 1923 by J.N. Bronsted and T.M. Lowry. It was an extended version of the Arrhenius theory. The definition of Bronsted-Lowry theory as an acid or base is not based on dissociation, but rather that an acid is classified as what we call a proton donor, and a base a proton acceptor. If we consider a hydrogen atom consists, in its most common isotope, of a single proton and a single electron. If I remove that electron, I am left with nothing but a proton. So an H+ can be considered a proton in terms of the species. Now in water, the H+ will not behave as H+ by itself, but as a combination of water with the extra proton, what we would call H3O+. This is referred to as a hydronium ion, not to be confused with a hydroxide ion, which is OH-. Hydronium is responsible for acids' general properties in solutions that we've talked about earlier. As an example of Bronsted-Lowry theory, if we take HCl and react it with water, we'll form H3O+ and Cl-. So we see here a transfer of the proton from the HCl to the H2O, forming H3O+. NH3, as a base, can accept a proton from H2O, forming NH4+ and OH-. So the H2O gives off H+ to the NH3, making NH4. Neutralization, according to Bronsted-Lowry, then, is a transfer of H+, or transfer of a proton from an acid to a base. Sodium hydroxide will react with hydrochloric acid, and we see that the H+ will transfer from the HCl to the OH of the NaOH, forming H2O. The leftover counter ions, sodium+ and chloride-, will combine together and form NaCl. Bronsted-Lowry theory will take solvent into account, whereas Arrhenius theory did not. The hydronium ion is a bridge between acids and bases. So the hydronium ion's interaction with water allows it to move through solution until it finds something to react with. Any substance that has a hydrogen is a potential acid according to Bronsted-Lowry theory. And likewise, any substance which has a lone pair is a potential base. Lewis theory is the most complete theory of the acid-base theories, and developed by G.N. Lewis. The definition of an acid-base in this is independent of any particular element. An acid is considered an electron acceptor. It takes an electron pair from a base. A base is an electron pair donor. This applies also to sharing of electrons. So if we're looking at a base will share its electrons between an acid and a base in some instances. So I can get a complexation or combination of the acid and base species bound together by that pair of electrons. In Lewis theory, the orbital overlap of low valence orbitals is what allows this to occur. Acids have low empty valence orbitals. For instance, beryllium trichloride has empty p orbitals, which are available for bonding. Bases have low valence orbitals which contain a pair of electrons as lone pairs. For instance, NH3 has a lone pair. So the lone pair in NH3 can be donated to the empty p orbital of BCl3, forming a bond. Neutralization, then, is a coordinate bond between an acid and a base. For example, NH3 and BCl3 can be coordinated together and combined by a pair of electrons between the boron and the nitrogen. Anything that has a lone pair can be considered a Lewis base. Most reactions which occur will occur by Lewis theory, because we have transfers of electrons which occur. Often, Lewis acids are substances which have 6 electrons. Things like BCl3 or AlCl3 have 6 electrons around the central atom. When they combine in coordination with the base, they wind up getting an octet of 8 electrons because of that extra electron pair which is now shared between the acid and the base. We apply this also to metal coordination. So for instance, tin tetrachloride can react with chloride ions to form tin hexachloride as a 2- ion overall. Many organic acid and base reactions require Lewis theory to explain how they work. Things which also occur in non-aqueous solvent or general metal coordinate complexes are generally explained by Lewis theory. Other than that, if we're dealing with aqueous solutions and generally protic acids, or things which have a proton, we'll often just use Bronsted-Lowry theory as a sufficient explanatory theory. Now, if we think about the way that NH3 would react with HCl, the H plus is a proton which is free to accept a pair of electrons. The NH3 has that pair of electrons, so coordination between the NH3 and the H plus with that pair of electrons forms NH4 plus. The same way we see a complexation here with SnCl4 and the 2 Cl minuses. And that's how we can explain the reaction of NH3 in terms of Lewis theory. Now, most of the acids that we deal with in terms of Bronsted-Lowry theory deal with what we call conjugate acid-base pairs. Bronsted theory will discuss these conjugate acid terms. A deprotonation of an acid will form a conjugate base. So HCl, losing its H plus, forms Cl minus. Cl minus is the conjugate base of HCl. If I were to protonate a base, I form its conjugate acid. So NH3 gaining an H plus forms NH4 plus as the conjugate acid of NH3. When I write a conjugate, to make a base, I will add H to the formula and make the charge more positive by 1. For instance, if I take HCO3 minus, I add an H, which becomes now H2CO3, and my charge goes from minus to 0. To form an acid conjugate, I remove the H and make the charge more negative by 1. So for HCO3 minus again, to act as an acid, I would take off the H plus, so I'm removing an H and decreasing the charge by 1. So I go from HCO3 minus to CO3 2 minus overall. If I look at this system then, here is a combination of an acid and a base together with the acid base and conjugate base connected. So the NaOH serves as a base. When it gains a proton, that OH becomes H2O as a conjugate acid because OH minus gains 1 H, becoming H2O. Increase the charge by 1, becomes H2O neutral. HCl will form Cl minus, losing the H, so we have Cl minus. Cl minus will then coordinate not coordinate complex, but will ion pair with the counter ion of Na plus. So Na plus and Cl minus will form an ion pair together, leaving the residual product as a salt. In a generic acid-base equilibrium, such that Ha plus B yields Hb plus A minus, a stronger conjugate base will generally be a weaker acid. So the stronger the base of the acid, so for instance Cl minus is a weak base, very, very weak base. Something like CO3 2 minus is a much stronger base. So H2CO3 as an acid is a weaker acid than HCl is. The stronger the conjugate base, the weaker the acid. Likewise, the weaker the conjugate base, the stronger the acid. A weaker acid tends to be more in its equilibrium towards the reactant side of the equilibrium. So something like H2CO3 will lie mostly towards the HA side of the equilibrium. Something like HCl will lie mostly towards the A minus side of the equilibrium.